So far in our prior lectures, what we have been looking at have been sort of developing an appreciation for structure as well as nomenclature so that we can describe the three-dimensional structures of molecules and we can discuss them in the context that we can give them names. So we've essentially established a language, both a visual language as well as an audible language and written language on how we can move into and discuss molecules. But what we are interested in, what we really want to be able to discuss, is how these molecules combine or how they form new molecules through chemical reactions. And probing chemical reactions is not, of course, as you can imagine, super straightforward because you cannot see bonds being broken or bonds being formed. But you can measure certain components of bond formation and bond breakage. You can also measure certain aspects of chemical reactions that will give you clues to how these things occur. And what we can measure is, say, for instance, in the conversion of methane into chloromethane. This is a reaction that does not occur spontaneously at room temperature. Neither methane nor chlorine gas are necessarily fun to be around. But if you mix them together and you shine light, which is abbreviated as H mu, or you use heat, which is abbreviated as delta, you'll make methyl chloromethane and you'll make hydrochloric acid, neither of which are fun to be around either. Now, how do we probe? How do we really discuss how these molecules, methane and chlorine gas, combine? And we can begin to understand the mechanism of reaction by observing how much heat is generated, how fast the reaction proceeded. Those two things will give us an idea of what sort of intermediate compounds. So on the way from going from methane to chloromethane, were any higher reactive species generated? Absolutely, most certainly there were. There's no magical way for methane and chlorine gas to combine without undergoing some sort of bond breakage and bond formation. And that means that some CH bond had to break and some Cl bond had to break. So there's some intermediate compound where there's a broken bond. So how do we know what those look like? And we can figure that out using these two things. We can also try to figure out if we can accelerate the reaction with a catalyst. So a catalyst will enable a reaction to proceed faster, or a reaction that's not even favorable to occur. It'll allow it to occur more so by lowering those really high energy intermediates or transition states that occur between starting material and product. And that means we kind of have to know what that intermediate or that transition state looks like in order to realize if there's an actual catalyst that can speed it up. And so really what we need to know, are there intermediates generated at all? And what do they look like? So let's go down and actually sort of pictorially describe what I mean by intermediate and transition state, because intermediate and a transition state are actually two different things. And the best way to illustrate these differences is with something called an energy diagram. All right, and in an energy diagram, what you have is it's essentially composed of two coordinates. One is potential energy, and the other is just simply called a reaction coordinate. And the reaction coordinate is some sort of amalgamation of structure and time. So how does a structure evolve over the course of a reaction? And at the beginning, there's starting material, all right? And starting material, in your particular case that we saw above here, that was methane and that was chlorine gas. And they have some sort of relative energy relative to your final product. All right, and you can see I've drawn your product at a lower energy relative to your starting materials, which makes sense because in most reactions what you're doing is you're typically going towards a final product that's lower in energy so that the reaction itself is energetically downhill. Okay? But in order to get to that product, it involves bond breaking and bond forming. And bond breaking requires an input of energy. So you have to have some sort of energy that goes into it. And in the particular case with methane and chlorine gas, you have, at least in the case of when you use light, you have some sort of bond cleavage event with chlorine at least, where your chlorine now is about to break. All right, it's not totally broken, but it's on its way. And the same thing actually can occur with methane, but the first initiation of chlorine is the weakest bond, as that's chlorine, and it's going to break. And actually it does break. And chlorine breaks in a very funny way. It makes a chlorine radical. Okay? And that chlorine radical is actually kind of stable. You can visualize it. You can see it. It does stuff. It's a real thing. It's a real compound. This that I've drawn up here, this exacerbated bond where the electrons are about, one electron is about to go here and one electron is about to go here. And you got to note that this is a half arrow, sort of like a fish hook, because that represents one electron. Remember, a full arrow with two arrowhead thingies. Like if it were this, that would be 2 electrons. Well, one electron is going to go onto one chlorine atom and one electron is going to go onto the other. And this very exacerbated bond, that chemical structure is at the apex of fury, about to release itself, and that's called a transition state. We can't isolate those. We can't even see them. They're hypothesized to exist based on very good and compelling evidence. But we can see that the chlorine radical exists, and that gives us very good evidence at the transition state. And this chlorine radical is an intermediate. And that's an intermediate on its way to the product, of course, right? And so you have this breakage, this chlorine, and then in order to actually form your final product, which is methyl chloride, that chlorine atom now, that's chlorine radical now, and he actually needs to go and do some kind of crazy chemistry on methane. So you have to have some sort of chlorine radical doing some abstraction with methane here, all right? And that abstraction is going to be formation of of HCl. There's all these kind of bond formations and their bonds breaking. I can try to illustrate like this chlorine is going to form a bond between that H, but this bond here is starting to break. This is, that looks like it's violating octet rules. This sort of bizarre structure is another higher energy transition state on its way to form HCl. And of course, as I said, there are 2 chlorines here, right? Because this is breaking up over here. So that means that as that's breaking, you probably have another structure here that's starting to form with that chlorine. You have some sort of stable intermediate chlorine radical, 2 chlorine radicals to be specific, and then that goes on and that forms another transition state where a bunch of bonds are breaking and forming, and then finally that just relaxes down to your product. So this gives you an idea, and this sort of tells us how this reaction happens. What happens in this particular reaction is you have to have some sort of initial breakage of the chlorine-chlorine bond. And this is actually what happens with this reaction, is you do form 2 chlorine radicals. And then these chlorine radicals are actually the high energy reactive intermediates that can now react with methane. Okay? So now the methane is able to interact, and you're able to start forming and breaking bonds with methane. And that then leads to a product. That is the mechanism of this reaction. And that mechanism does tell you a lot about how things happen in a particular reaction. Now, this reaction coordinate, this reaction energy diagram, actually can tell you a lot about a different chemical reaction. It can tell you about the forward process of a reaction, how long it takes to go that way. So that's your reaction kinetics, your rate. It can tell you the relative proportion of the number of reactants that are still at starting material and product. There's a lot of stuff going on here. So let's try to individually unpack the energy diagram, all right? So one particular thing that the energy diagram helps us understand is something called equilibrium. An equilibrium is a thermodynamic constant. that in a reaction you can have a product and it'll undergo some sort of reaction. There might even be an intermediate and a transition state, and you end up with a product. Now, there is a discrete level of energy that exists between here and here, and if that energy is not terribly high, the process that drove you this way over the hill to a product can actually still go backwards. There's still a possibility that that just goes back over that hump and that goes back down here, right? So that is what equilibrium sort of describes, is if you look at the relative differences in this energy, what we call delta G, that's the energy difference between starting material and product. That delta G is directly related to the equilibrium. There's a direct relationship between the delta G and equilibrium. Usually, with all confounding variables set aside, the smaller the delta G, the larger your equilibrium, the more likely you're going to have starting materials in addition to products. All right. And in this particular reaction, we draw this out as essentially if you have two starting materials, starting material A and B, there's some sort of reaction that drives you to C and D, for instance. So in this particular reaction, I've got A plus B, and that's going to C plus D. And as I've drawn here in my process, I've got one reaction that's going forward, and then I've got another reaction that's going backwards, right? And that relationship, the amount of going forwards and backwardsness, right, that is related directly to K equilibrium. So this ratio is simply, there's an equilibrium constant that is associated with the amount of products. So we put this in brackets. That means concentration of product over the concentration of the starting material. And when this reaction is going, that is a constant, and that constant is defined by big K, sometimes big K with a little equilibrium down there, okay? And that tells you, all right, so that tells you from essentially hopefully two knowns. In this particular case, this is kind of helpful because in a typical reaction, you know how much you added, at least I hope so, when you measured it out on your balance. You may even be able to find out how much your products are. Say your starting material is one color and your products are a different color. You can actually look at the spectra and determine what the relative concentrations are of these. And then you just sort of plug them in and you can get a K equilibrium. So that K you can actually use to determine the difference in energy between your starting materials and products, because delta G is directly related to K equilibrium, right? So how? Let's consider delta G. So what is delta G in terms of if we start to mathematically define delta G? Delta G is quite simply, delta G is something called the Gibbs free energy. All right, and the Gibbs free energy is very simple. It's just the free energy of products minus free energy of starting materials. All right, so that is pretty easy to appreciate, I would think. And so how is K equilibrium related to that? And if we use standard free energy, delta G, K equilibrium is related to that by this equation. Negative delta G over RT. All right? So what we're looking for in this particular case is if we have a process where delta G is negative, and these are some good diagnostic criteria. So if a delta G is negative when you solve this, then that means that this reaction releases energy. And if it releases energy, then that means that the reaction occurs spontaneously, because that means that you don't need to continuously put in energy. If you need to pump energy into something, as soon as you stop, the reaction goes backwards. But if the reaction releases energy, you don't have to pump energy. In fact, it emits energy. That means that the reaction will occur. It's what's called a spontaneous reaction. And so delta G, just the very sign of it, is actually quite useful. So when you solve for this equation, if you get a delta G that's less than 0, you have a spontaneous reaction. If you have a delta G that is equal to 0, then you have a system at equilibrium. All right? And equilibrium means that there is no more chemical reaction occurring. All right? And let me move this out of the way. In fact, let me move all this out of the way so that I can. And then, of course, if you have a delta G that is greater than 0, you don't have a spontaneous reaction. It's not spontaneous. It's not spontaneous in the forward direction, but spontaneous in the reverse direction. So what I've drawn up here is an example of an energetically spontaneous reaction. So, and these are totally arbitrary values. If that's 10 and that's 8, I'm sorry, if starting material is say 10 and your product is 8, because that's 10, because it's up higher than this is down here. The 8, that's 8 minus 10, that equals -2, which means that this reaction is spontaneous. Okay? So that would give you a clear indication that you have a spontaneous reaction and that if you mix these two together over some period of time, and I'll be honest, that time could be infinity, but it will happen. It could be in a couple seconds, it could be in infinity, it will happen. It doesn't tell you when it will happen. That's not what this equation does. You know, there's temperature associated with this, but no time parameters, which means this entire thing is totally independent of time. Equilibrium has nothing to do with the amount of time something happens. It'll tell you if something will happen. It's invariable that we will all eventually reach equilibrium ourselves. That means all of our cells will have reached a stopping point. We'll be dead. We don't know when. There's no associated kinetics of our own death that we can really figure out. And as morbid as that is, it's sort of the same sort of thing. We can all be guaranteed eventually we'll all die, but we will never really know exactly. And that is what thermodynamics is. We can be assured that this will happen. We cannot be assured when. But K-equilibrium is often written in a more convenient way, or this delta G. If you directly solve for delta G, there are other expressions for this. So other expressions for delta G using the equilibrium constant can be delta G equals negative RT ln K equilibrium. So that would give you a fairly straightforward way of solving for delta G. All right. Delta G itself, the Gibbs free energy, isn't just a product of equilibrium. Gibbs free energy actually has associated energy. So what are the energies? Like, what are the energies that are associated with delta G? Equilibrium, that's a consequence of delta G. That's not actually an energy that we can measure. What are energies we can measure? And what we can measure are essentially heat. We can definitely measure heat. We can determine how much heat is generated, how much heat is absorbed by a reaction. And so delta G is composed of two terms, actually. So delta G, that's actually equal to the change in the amount of heat, the change in enthalpy of a reaction. It is also correlated with this temperature-dependent entropy term, T delta S, okay? And temperature and entropy and enthalpy are all associated with your Gibbs free energy. And often we write these little dots up there to be perfectly clear that we're talking about Gibbs free energy in a controlled system that is 25 degrees in 1 atmosphere. So roughly room temperature, roughly at sea level. So each one of these terms, what exactly do they mean? Hopefully this is a bit of a review. We should remember that this is enthalpy. Enthalpy, all right, that's the heat of a reaction. Where do these heat of reactions occur? From bond breakages and bond formations, all right? So in an exothermic reaction, so a heat is evolved from the reaction. The heat is given off of a reaction when the reaction is a negative delta G. So you have an exotherm. The heat comes off, and that's usually what you would call a delta G that is negative. This reaction up here, for instance, is an exothermic reaction. It would emit heat because, as you see, the delta G is negative. It's an exothermic reaction. You can tell, requires heat to go to this, but eventually you get heat out of the reaction. An endothermic reaction would be exactly the opposite. If we're going from product to starting material, this requires heat to work. This requires some amount of heat to suck heat out of the universe in order to get back over there. That would be an example of an endothermic reaction, all right? So in the enthalpy, you can have either exothermic, and you can also have an endothermic reaction process. Now, the entropy term, that's an interesting term. Entropy is actually a measure of freedom of motion. It's more of a statistical component. So entropy, in its basic sense, is chaos. The more chaos, as far as the universe is concerned, the better. All right? And reactions tend to prefer, really they always prefer, a more freedom of motion. They prefer to be able to do more stuff. The more freedom of motion you provide a molecule, the more chemical space it can sample. So if you remember from a previous lecture, we had discussed how neopentane is a gas. We had discussed how it evaporates at very low temperatures, whereas pentane itself, 1, 2, 3, 4, 5, this actually is a liquid at room temperature, and this is a gas. And the reason why is, even though they contain the same number of atoms, is you have an entropic argument that energy can be involved in just flipping these things around. And so in a solution, eventually you have to get them into the right sort of physical orientation to minimize interactions with other pentanes for them to evaporate. You can rotate these around, and that doesn't change the geometry of this molecule at all, because you're just sort of rotating around hydrogens, and there's really no change in the physical shape of that molecule. Consequently, just from the fact that this has more chaos that it can sample, it requires more energy to pump out of the system to evaporate. And so organic reactions always tend to prefer entropy. And you'll notice just in my example, that's heavily temperature dependent, just like the more chaos you have, the more temperature you need to start pumping it out, all right? Roughly speaking. Now, of these two terms, entropy, that's a very tough thing to measure. Entropy is usually always inferred from delta H and associated delta G's that you can measure. But delta H is directly measurable. And if you get delta H, you can experimentally determine it through something called calorimetry. But the enthalpic term of a reaction, the delta H, is controlled by the energy of the bonds forming minus bonds breaking. Okay, so the entropy is bonds forming for minus bonds breaking. And so for a reaction to go forward, the energy associated, and this is not the number of bonds, this is the change in energy and the change in energy associated with them. You have to look at the energy that you get out of forming bonds and subtract it from the energy associated with breaking bonds. And a lot of these are known. The energy associated with a carbon-carbon bond breaking is pretty well known, and the associated energy with a carbon-carbon bond forming is pretty well known. And you can actually generally, what's called a priori, that is, before you even do the experiment, you can calculate these sorts of things. You can calculate them from known bond association energies. All right. So this is a solvable component, is that you can find the actual value of delta G because you can measure directly delta H by heat through isothermal titration, calorimetry, or through just knowing bond formation and bond breaking. You could look those up on a table. That gives you delta H. You can measure delta G from the equilibrium constant. All right, so K equilibrium can be plugged in to give you delta G. So now you have delta G, now you have delta G, now you have delta H, and from those two, you can then solve for the entropy term. All right, and so that's how you can fit all these things together experimentally into one cohesive definition. Okay, now I had mentioned that all of this, in all of this process, this tells you whether it's possible. It doesn't tell you how fast. It doesn't give you any idea of an actual rate. And that is because thermodynamics and kinetics, there is a wall. It's a porous wall, but there's a wall that separates thermodynamics and kinetics. And they use tragically confusingly the same letter K. All right. So if we wanted to discuss not the equilibrium, not the energetics, not the heats, but we wanted to discuss time, we wanted to discuss the rate of a reaction, we would have to look at the rate equation. All right. And a rate of reaction just occurs, not necessarily your product and starting material ratios, just if you have A plus B, and we said this is an equilibrium, and they go to C and D, how fast is that? What is the rate of that reaction? And the rate of that reaction, all right, is some lowercase k rate constant times the concentrations of your starting materials. All right. So in this particular reaction, as I've illustrated it here, A goes to B. So your starting concentrations of A times the concentration of B times some measurable, identifiable, but yet unknown constant K, lowercase k for rate, your rate constant, is what gives you your overall rate of reaction. That'll tell you how fast something is going to go, all right? And on your energy diagram, if we draw our energy diagram, that rate is actually illustrated having nothing to do with this bit. Actually, rate is associated with something called transition state theory. This distance between your starting material and the highest hump of your transition states, whatever that is, not this one, because that's the highest, that's the highest, right? That is the amount of energy you need to get a reaction going, your energy of activation. And if you know your energy of activation, you will know your rate. You will at least know your rate constant, okay? And your rate constant is defined by something called the Arrhenius equation. And that equation looks at your Kr and puts it in terms of some constant called the Arrhenius pre-exponential factor. And that is a constant that's directly related to the reaction itself. So every reaction has its own A. All right, and that you just have to experimentally determine. And that's the pre-exponential factor, so you do have an exponential. And then that's where your EA comes from, as your EA comes in here. and that is your gas constant times temperature, RT, all right? And that EA is the minimum kinetic energy required to cause the reaction to proceed. That's what we would call the minimum kinetic energy needed for the reaction. All right, and what exactly does that mean in terms of minimum kinetic energy? Well, let's imagine in this particular case, A and B are spheres, right? A is an orange sphere, B is a green sphere, and then they come together to create something else. And so how does that exactly happen? You have to imagine that these two spheres in your reaction conditions, in your reaction coordinates, are just kind of like zooming around. They've got a lot of kinetic energy associated with them, and they're on some trajectory and they're flying around. And they're not all going at the same speed, actually. They are going at different speeds. Some of them are going actually a bit slow. Some of them are going a bit fast. And that's sort of what temperature is. Temperature is some sort of distribution of how much energy, how much speed these guys have. So if we want to bring these down here, let's discuss this in the context of what this energy of activation actually means. So if I say you have some sort of temperature or energy or whatever, what have you. You have a distribution of atoms or these molecules that are going at different speeds. So if we just look at this one, you could have an orange ball, that's zooming around and that's just puttering, right? And then you've got another one that's just, that's like, whoa, how do you even draw that? That's a comet, right? And that is just like on fire. It's going so fast. And your temperature kind of gives you an idea of what the proportion is. Obviously, at very high temperatures, you'll have more of these little fast comedy guys just smashing into stuff. And at low temperatures, you'll have more of those little things that are just puttering around. And in order for a reaction to occur, you have to get over some minimum amount of you have to get as many towards, however fast they need to be, right? So if you have some sort of reaction diagram, let's say, let me do this. All right, yeah, 300K. This is your proportion. And it's some sort of large exponential tail, right? And at room temperature, this is your proportion, where over on this side, you've got, little puttery things, and maybe it's got like a little cane and it's walking around. And it's like, oh, my back, ow, ow. Right? And then over here on this side, you've got, your extraordinary speedy little race car thing over here. And it's got like a thing here and, and it's just insanely fast. And that's just going so fast, right? That is your proportion. So at 300 Kelvin, you have some distribution of things going at various rates. Except I tell you, the only things that are going to actually undergo a reaction are here. Okay, so they have to be on this side of the energy potential in order for it to work. So this is just your energy, E. And that energy is related to temperature. So if you want more stuff, and this is actually pretty intuitive when you think about it. If you want more stuff to react, you have to push it over here, right? So if we just heat up the reaction a little bit, if we say we wanted to do this at 373 degrees instead, our entire, let's use a different color. Maybe not quite as bold as that. No, already selected orange. Let's go with blue. We wanted to do something at 300 degrees. Now our proportion of molecules is now over like that, right? So a substantial amount is still going. That's still undergoing some reaction, like all of this over here. All of that is now sufficiently energetic. But you still have a population over here that hasn't quite hit that. There is some sort of dynamics, because obviously if a super speedy molecule goes and it smashes into a super slow molecule, what do you get? You end up with actually two average speed molecules. Then you get two average speeds if two of those collide. So really, in a chemical reaction, there is some sort of give and take. Sometimes the little slow guys run into the super fast ones, and then they sort of putter out. But really, in order for a reaction to occur, you need one of these super slow ones, or one of these average speed ones, to run into an average speed one of your starting materials. So these two actually have to collide, right? Two orange ones colliding actually does nothing. They just bounce off each other. But once these two collide, and assuming they have a sufficient amount of energy, they will go on to form your products, C plus D, right? And so as you increase temperature, you increase the relative proportion, the population of atoms that are able to undergo that reaction. All right? And that is essentially what kinetic theory is. That if you increase your temperature, you increase the number of atoms capable of getting over that hump. So that takes us all the way back up here. That this really is just sort of the probability of two atoms running into each other. And that does have something to do with probability, and that probability is built into your entropy term. But it also has something important, that these two atoms have to be going fast enough. They have to have enough energy. And I should actually, I guess, switch in your colors, which is not going to be helpful. But if I put the colors back, that there has to be some probability. And that probability, like I said, was your entropy term. But just as importantly, there has to be some amount of speed. They have to be going above a certain threshold of speed. And those have to be running into each other at the right sort of time in order for them to actually proceed forward. So that is essentially what rate is. Rate has way more to do with energy. Because of course, as you increase your temperature, you also increase the probability that they're going to run into each other. But you're increasing the energy. And the more energetic molecules you have, the faster, and that's an important part, the faster they go over the hump. Okay? And so that is your distinction between your speed and your thermodynamics. All right? Now, adding a catalyst is kind of funny, right? Because a catalyst actually lowers this rate. All right? A catalyst, what a catalyst does, if you throw a catalyst in here, you have something that, say, does a couple of things. One, a catalyst can lower the actual energy of one of these things, so that the reaction just occurs actually at a lower energetic barrier, right? So you could have a catalytic process that now lowers that energy of this first state. That's a catalyst. And if you have a catalyst and it lowers that energy, and you have actually now a new term, a much smaller term now called kcat. So if you throw a catalyst and the catalyst goes in, because you've lowered the energy necessary to get over that transition state, this catalyst essentially lowers it. That means you need less energy to go over, and that means that the rate will go faster. So a catalyst exerts its influence by lowering that energetic barrier below the threshold necessary to go, all right? And you'll notice what I've done here actually is I've lowered this barrier a little bit lower than this one. So actually now, the whole process, the actual amount of energy necessary for this reaction to go is no longer dependent on whatever this transition state is. It's in the catalytic reaction, it is now dependent on this transition state. So that means at the very minimum, if you want a product here, you have to get enough energy to get over this barrier in my catalytic reaction. So in that sense, my catalyst has actually sort of changed the energy landscape and what considers the more significant process in this reaction, whatever this transition state is right here. All right?